All right, so let's talk a little bit about causality. So we've ran 2 A/B tests today, and in both cases, we rejected the null hypothesis. We said that babies born to mothers who smoke do weigh significantly less, and we said that the Patriots footballs dropped significantly more in pressure. However, we were cautious to say that even though we rejected the null hypothesis, this doesn't mean that we established causality. It doesn't mean that smoking causes lower birth weight. It doesn't mean that the Patriots actually cheated, although I think most people think that they actually did. The reason is that there could be confounding factors. There could be other reasons that we saw the drop in pressure or the lower birth weight. For example, instead of smoking, it could have been caffeine that caused lower birth weight, and caffeine was correlated with smoking. So that's why we saw smokers having lighter babies. Or it could have been that the Patriots stored their footballs incorrectly in a way that caused damage. So remember that if I want to establish causality, what I want to do is run an RCT, a randomized controlled trial. The studies that we saw before, the study of mothers who smoke, that was an observational study. That's the key word, observational. That means I just gathered data that I had lying around. Okay. In an RCT, in contrast, I assign people to treatment and control groups. I tell one group of people to smoke, one group of people to not smoke. And remember, I can't really do that here. It's not very ethical. So the key thing here is that if I have an observational study, rejecting the null hypothesis doesn't support causality. But if I have an RCT, rejecting the null hypothesis does support causality. And so it's very powerful. So let's remember why rejecting the null doesn't support causality in an observational study. So suppose I want to examine the link between chocolate and heart health. Does chocolate help your heart? Does it hurt your heart? So I do an observational study. So this is an observational study, not an RCT. And we see that chocolate eaters tend to have healthier hearts. So here's my data set here. And I have 1 if the person eats chocolate, 0 if they don't. And then I have 1 if they have a healthy heart and 0 if they don't. And what I see is that 4 out of 5 people who eat chocolate have a healthy heart. Only 1 out of 5 people who don't eat chocolate have a healthy heart. So this seems to suggest that, hey, eating chocolate, that's going to cause greater heart health. But remember, this is an observational study, and so I can't conclude that, and here's why. So suppose it turns out that chocolate eaters are more likely to consume caffeine, and it's actually caffeine which actually helps the heart health. So this is what it might look like. We didn't observe this in our study. We only observed these 2. But here's what's going on behind the scenes. Okay, it's actually that whenever you consume caffeine, you have a healthy heart. You see, so whenever I see a 1 over here, I'm more likely to see a 1 over here. And whenever I see a 0 here, I'm more likely to see a 0 over here. And because eating chocolate is correlated with consuming caffeine, this is why I actually see the difference. Okay, so that explains why an observational study doesn't help. But why does an RCT help? Well, the idea is that if I run an RCT, I'm randomly putting people into groups and giving them chocolate. And randomization ensures that caffeine consumption is basically fair or divided equally between the 2 groups. So that kind of mitigates the effect of the confounding factor. So here's my RCT that I've ran. I've randomly put people into groups and given some of them chocolate and some of them did not give them chocolate. And so now you see that the people who consume caffeine are kind of distributed roughly equally between the 2 groups. And remember, it's caffeine, not chocolate, that's actually causing the good heart health. So at the end of the day, I see that there isn't much of a difference now between the people who consume chocolate and the people who didn't. And so I would say that there isn't a significant difference in this RCT, and chocolate does not cause good heart health. If I were to rerun the study and use caffeine as my treatment, then I would see a significant difference, and I would say that this does look to be causal. So let's take a look at an example, and where we often see this, see RCTs and find them very useful is in medicine, where we can give a treatment to a group of people and see if it has any effect. So let's take a look at chronic back pain. So you may have heard of something called Botox, the the medical term for it is botulinum toxin, and it is the most acutely lethal toxin known. So actually, this is a very scary toxin. It can cause like locked-in syndrome where you're paralyzed, and people actually used to get botulism from botulinum toxin from canned foods. They would can their own food, and they wouldn't, pasteurize it or whatever process it is to kill everything in there, and it would get botulinum toxin inside. This would grow, and it would cause the can to like expand. And so they would say never eat something from a can that is kind of like full of air, because that means there might be botulism inside. But as soon as botulinum toxin contacts oxygen, it kind of dies or it doesn't grow. So it's okay to eat outside. But in any case, back to the example here. So it's a very lethal toxin. However, people actually use it in medicine to treat muscle disorders and also for cosmetic reasons. Botox, you inject it and prevents wrinkles and stuff like this. So the question was, hey, can we use Botox, botulinum toxin A, to treat lower back pain? So what this group of doctors did is they gathered 31 patients with back pain, and they randomly assigned them to control and treatment groups. The control group received placebo. They just injected them with salt water. Treatment group received botulinum toxin. After 8 weeks, they calculated the number of people who experienced relief. And here's the data. Okay, so we got a 1 in this column if the person achieved relief, 0 if they didn't, and we have whether or not they belong to the control group or the treatment group. Okay, so we had 31 people. We can see, for example, this person belonged to the control group, and they received some relief by being injected with salt water. But, maybe it was because they did yoga or something like this and also got relief that way. Okay, so how many experienced relief within each group? What was the proportion? So I'm going to group by the group they were in, calculate the mean. I see that 60% of people in the treatment group achieved some relief. 12.5% in the control group achieved some amount of relief. So it looks like there was a clear benefit due to treatment. Now, was this just due to chance? Let's run our permutation test and see. So let's call group A our control group, group B the treatment group. Our null hypothesis is that the results come from the same distribution. The alternative is that no, group B experienced more relief. Our test statistic is the difference in proportion experiencing relief. So let's run this. Same pretty much as before. So our test statistic, our observed test statistic is 47.5%. Is that a large difference? Let's run that permutation test with 500 repetitions and see. So it's the same playbook as before. I'm going to, on every iteration, permute my data. In this case, I'll permute one of the columns, doesn't matter, the result. Assign it back to the table, compute the test statistic, append to an array of differences. Okay, so I did that. Now let's look at the distribution. So remember, the difference we saw was, I don't actually need that. Here's our distribution. We saw that on average, the difference between the groups was 0 under the null hypothesis. Remember, the null hypothesis is there is no difference between the groups. Okay, so the 0 makes sense. Sometimes just randomly, we would see some difference like 20%. But seeing a difference as large as 45% was pretty rare. In fact, if we calculate the p-value, we see that it's a 0.006 probability. So that's less than 1% chance. Okay, so it looks like this is significant. Okay, in fact, it is significant. One thing I'll point out here is we're calculating differences greater than or equal to observed difference. Why the greater than equal? Remember, what we want to calculate here is the probability of seeing something at least as extreme as what we saw. So you have to figure out, what does it mean to be extreme here? This depends on your alternative. If your alternative is just difference, doesn't matter if you're greater or less than. If your observed difference is positive or negative, then the probability would be calculated by looking at both tails of this. Extreme would be just far away from the middle. But in all our alternative hypothesis, the extreme is a greater than 45% difference in effectiveness. Okay, so in this case, we're only looking to this side. We're calculating the probability here. And we see if I calculate the p-value, it's 0.006%. Or sorry, 0.6%, because multiplied by 100. Okay, so in conclusion, we're going to reject the null hypothesis with a high degree of confidence. How much confidence? We give that p-value to express how confident we are. Now, in fact, because this was an RCT, because it was a randomized controlled trial, the cool thing is that this is evidence that the treatment actually caused the improvement. It was the treatment itself which did it. It was the injection of botulinum toxin. Okay, so that's very cool. Okay, so we can establish causality, and that's awesome. Now we have to be even a little bit more careful. You have to dig into the results here. I'm not a doctor, so all of this is just conjecture, but the botulinum toxin probably was the result of the improvement. However, suppose that I have a saline solution that's just salt water. The botulinum toxin, I might need to suspend that in a like another chemical for it to be injectable or whatever. Maybe it was that other chemical that actually caused the effect, right? Not the botulinum toxin. So in order to be very careful, you would have to have that same chemical in both the saline and in the botulinum injection. So you have to be careful about how you actually run the experiment, because whatever differences there are between the two groups, it could be any of those differences that were causal. So you have to make sure that the only difference between the two groups was that one received botulinum toxin, the other received saline. There was a question on the exam kind of about this, right? It was if you have a teacher who has a new strategy for teaching, and they apply it to a group of kids, and then it's an RCT, so they randomly select kids, and then there's another group, or they have the traditional approach to teaching, and they give that to the control group, and they see that there's a difference between the two groups. The way they do this is they have the teacher A teach group 1, teacher B teach group 2 with the traditional way. You can't conclude necessarily that it's the type of teaching, it's the teaching strategy that was the difference between the two, because the other difference between the two groups was the teachers. Could be that teacher A is just a better teacher than teacher B, no matter what strategy they used. So you have to be careful that the only difference between the two groups is the thing that you're trying to assign causality to.